Hi everybody, so today we're going to walk through the rest of section 2 of chapter 1. There are going to be lecture questions for you to pause the video and answer on a sheet of paper, and then I'll ask that you upload those as proof that you've actually watched our lecture today. Just to recap what we were talking about last time we were together on Friday last week. The water molecules that we were discussing, we had solid, liquid, and gas. And with water, since things are a little bit weird, the solid tends to separate, the molecules tend to separate from each other and form like a lattice. And that is why water tends to be less dense in the solid form than the liquid form. Remember that we talked about the different types of motion in each of these phases, and we talked about kinetic energy in each phase. And we said that from solid, we had the least amount of kinetic energy. The molecules really aren't moving, they're just kind of vibrating in place, but they are still in a moving state. In a liquid, things move a little bit more. They kind of slide past each other and around each other and can associate with each other a little bit differently than they do in the solid state. And then the gas state, they are the farthest apart. They kind of move around freely and they're really crazy and fast. And we said that kinetic energy progressively increases from our solid to our gas. From there, we were talking about what are the signs of a chemical change, and this is one of the things I wanted you to answer. So with a chemical change or a chemical property, we say that a chemical property, which is slightly different than a change, is going to be related to a substance's ability to undergo those changes that will make it into a different substance. In other words, chemical property is whether or not something is combustible or able to be burned, might be whether or not something is able to be reacted with something else. And when we talk about these different chemical properties, one of the things we are looking for is signs of a chemical change, and we're going to see some examples of that here in the near future. But basically where a substance, say water, becomes something different than what it originally was, like hydrogen or oxygen gas. And that is actually what we call electrolysis. From here, we want to talk about how chemical reactants and products are involved in these different chemical changes. So basically what we're saying is reactants are the things that are going to react together, and then products are the things that are going to be formed over the course of those reactants reacting together in a chemical way. Here we have our example of the formation of carbon dioxide, where we take carbon and oxygen and we form carbon dioxide. And we know that this reaction has occurred because carbon dioxide is a gas, and so when we know a chemical change is occurring, we're looking for specific clues that it has actually happened. Here, we're going to see that there are 4 different ways that we can actually see that a chemical change has occurred. The first is going to be that bubbles appear, right? So we see that a gas is formed. If we add 2 things together and a gas forms, we know something chemically has happened to change the original substances that were added together. The next thing we look for is a precipitation, in other words, a solid being formed. If I had 2 clear liquids together and this bright yellow solid forms, then I know that something has happened at the chemical level to change the original substances into something new. Next is going to be the formation of heat or light. That would actually indicate that a chemical change has occurred. And then another one that we would look for is color change. So here we have phenolphthalein and ammonia, and those are both just kind of fancy terms for chemicals that change color when they're added together. The color change from nothing to pink is in fact a chemical reaction. So color change, solid being formed, heat or light, and bubbles are the 4 major versions of chemical changes that we're looking for. Which brings us to our first lecture question. You can go ahead and pause the video and answer the question. And if you need to go back, you can, but please make sure you get this one answered on a piece of paper. There are 2 more, so this is just the first. And I'm going to go ahead and continue. All right, the next one is an example of a chemical reaction. Here we have water that gets passed through an electric current, and when it does that, it becomes oxygen and hydrogen gas, respectively. This is a famous type of reaction. It's called electrolysis. This is one that you'll see over and over and over again, but it's how we can actually create hydrogen and oxygen gas from just water molecules, which is something we have an abundance of. From here, we can talk about what is the difference between chemical and physical properties. For instance, we have mercury oxide, which when it is heated is decomposed into mercury and oxygen. And we know that those 2 things are formed because we're seeing the production of bubbles up there on the right where the oxygen is being shown. Here we're just looking at what is the difference between a physical and chemical property. So if we just examine oxygen, we know that oxygen itself has the physical properties of it being colorless, it has no odor, and we know that we could dissolve it into water. Some of the chemical properties are that when it is in contact with metals, it can rust, or it can oxidize, if you will. Also that it actually supports the combustion phase. Okay? Some of the chemical properties of something like mercury oxide are going to be that it decomposes when it gets heated to a certain type into mercury and oxygen gas. The physical properties are just exactly what you think, what you see, what you hear, or what you smell. Not hear, sorry. And what other things that you can observe. So remember that physical properties tend to be more observations of a substance that you can make without changing the substance itself. So in other words, color, odor, its ability to dissolve or not, what temperature it melts or boils at, what temperature it freezes at, things of that nature, okay? Same thing with mercury. We've got some physical properties, just kind of, look, it's this color. Look, it is in this state at room temperature. It's able to be formed and can be cut with a knife. It's very soft. Those are all going to just be physical observations of what mercury looks like. All right, next is going to be energy and changes in matter. So when we talk about energy, one of our major indications that energy is around is heat or light. So just remember that when we talk about chemical reactions, a lot of times this is a really good observation of something that happens when you change a substance from one to another. Very common version of this is, of course, combustion. We've talked about it, where something explodes or something gets lit on fire. When you burn wood, that's combustion, and so on and so forth. Energy is always going to be involved no matter what type of change we're going through, but the most common form is when we are observing energy from chemical changes. And one of the major things to remember, and you've all seen it before, is the law of conservation of energy states we cannot be creating energy and we cannot destroy energy. It must be conserved. So for instance, if I'm eating a piece of bread, the energy I get from that bread gets recycled and makes it so that I can walk up the stairs or something of that nature. That being said, we cannot just destroy it. It doesn't just disappear. So think about like when you are putting gas in your car, or when there's gas in a car of some kind. When you're using that energy by moving your car, that energy is going somewhere. It's being converted into mechanical energy to move your wheels. That energy in your wheels is then converted into thermal energy into the road, or into movement energy, kinetic potential, etc. Okay, so just remember that all energy is conserved. Just because you may not know where it's going doesn't mean that it's disappearing. Okay, and that brings us to lecture question 2. Go ahead and answer the question. You do not have to write the questions, just write your answers. You can put lecture question 1, lecture question 2, lecture question 3, and when you're done, you can go ahead and move on. Remember, you can always pause. All right, next is going to be the classification of matter. So here we see a flow chart, right? And we've talked about this flow chart before, just kind of mentioned it in class before. This is one that can help us identify what type of matter we're dealing with between mixtures and pure substances. So for instance, if I want to start, the first question I'm going to ask myself is, can whatever I'm dealing with be separated? And the answer is yes. That means it must be a mixture. The next thing we're going to ask is it a uniform composition? In other words, can I see parts or can I not see parts? If it's uniform in composition, then it's a homogeneous mixture, aka think about something dissolved in water. If you can't see the thing that's being dissolved, then it's a homogeneous mixture. If you can still see the thing being dissolved, then the composition is not uniform. It is considered a heterogeneous mixture. Think wood, think granite, think chocolate chip cookies, and things of that nature. And then on the other side, we have if it is a non-separable material, we have a pure substance. Next thing we're looking for is, can a pure substance be broken down into smaller parts, aka different atoms? If there are more than one atom present, then you know you have this compound. If there's only one type of atom present, then we know we have elements. Okay, this is how we just read the flowchart. From there, we have just a visual of the flowchart. Same type of thing. We're looking at a pure substance has one type of atom or two types of atoms, and if we wanted to, we could do something to break down those atoms into individual parts, or if we can't break them down into any other types of atoms, it's just one type of atom. And then a mixture, we've got homogeneous and heterogeneous. With a heterogeneous mixture, we can see the parts. So just kind of keep that in mind. All right, from there, we have formal definitions. So a mixture is going to be a blend of two or more kinds of matter. Could be something that's mixed together physically. No matter what type of mixture we deal with, since it's just a physical mixing, we can typically separate them. Now, with homogeneous mixtures, a lot of times when we want to separate them, we have to use a very specific method. We might have to heat, or we might have to use energy-based methods. With heterogeneous mixtures, we do not have to use energy-based methods. Think we could filter. Okay, we could filter the sand from the water by just putting a piece of filter paper or a coffee filter between the sand and the water itself. And then we could separate the water into one part and the sand into another. With heterogeneous mixtures, remember that we're looking for non-uniform composition. With homogeneous, we're looking for uniform composition. Think anything dissolved is going to be a pretty uniform composition. Think anything you can actually separate. If you let it sit there for a while and it settles, it's a heterogeneous mixture. Okay? Here we have some examples of silicon dioxide in water, which is really just a fancy term for particles that are in salt, or in sand. And then sugar molecules like glucose are going to be indistinguishable from the actual liquid that it's dissolved into. Okay? From there, we want to talk a little bit more about pure substances. Fixed composition means they cannot be separated by anything other than chemical or energy-based methods. So if I want to separate the carbon from the oxygen and carbon dioxide, I'm going to have to do a chemical reaction to do so. And that means I'm probably going to have to put in some kind of energy, or I'm going to have to remove some kind of energy. Our pure substances are going to differ from them in a few different ways, but energy-based removal methods is the big one. Every sample is going to have similar characteristics. Every sample is going to have the same composition. So if I have a sample of water, and then I get a different sample of water from a different source, they should still have the same composition in both. And they should still both freeze at 0 degrees Celsius. They should still both boil at 100 degrees Celsius or 212 Fahrenheit, and so on and so forth. And the last thing is the percent by mass, which is the amount that is hydrogen and the amount that is oxygen, should be the same no matter which sample I'm looking at. Okay? From here we can talk about how lab chemicals and purity are determined. And this is kind of like a side note in this chapter, but one of the things to know is that when we use chemicals in our lab, a lot of times they have been tested and have been analyzed to actually figure out what is in them, and if what is in them is going to be what we consider impure. So here we have an example of zinc nitrate. When it was certified, they went through and they tested for a bunch of different stuff to make sure that it was a pretty pure sample. This is not a 100% pure sample, but it's pretty close. And it tells you what else is in there. Now, a lot of times when we talk about different types of purity, one of the things that we want to note is that what chemical standard are we meeting? Pharmacopoeia means that you are making pharmaceuticals with it, and that is kind of like the minimum that you have to have in order to get like pharmaceutical products on the market. You've got FTCs, so food and chemical codes. That means that it meets a certain standard for consumption. You've got primary standard reagents, which are pretty important to chemists. We have to know that they are pure to like 100%, so that is the purest type of standard. So just understand that there is this thing referred to as a level of purity, and all chemicals are not necessarily pure. All right. Last thing to talk about in this particular section is going to be different types of mixtures, just kind of giving you some examples of different kinds of mixtures. You're going to want to study on what homogeneous versus heterogeneous means. Remember that one of the good indicators, one thing I would always indicate or ask you to think about is, if I let it sit there for a really long time, would it settle out? Would it settle by itself? Or the other thing you could think about is, if I put it through a filter, would anything filter out? And the answer is, if the answer is yes, then that would be a heterogeneous mixture. If it settles, it would be a heterogeneous mixture. If you have to shake it before you eat it or drink it, that is a heterogeneous mixture. If you don't have to shake it before you eat it or drink it, then it's considered homogeneous. Okay? All right, so your last question of the day is going to be this one. When you are done, please go ahead, go back on the Canvas and submit this in the proper assignment. I'll make sure that it is available for you. It should already be available for you, but if it's not, please do go find it. What is the difference between a homogeneous mixture and a pure substance is your last question. All right, that's all. Have a great day.